Hi, gang, Mass 6610. You may notice right off the start of the video that I have a new document camera. I finally got the new one in. Apparently, they're hard to get these days because so many people are teaching remotely. So we no longer have the big old black glob of stuff up there, whatever that was. But it wasn't really a glob, it was just a defect on the screen. So anyway, looks much better. I think you'll have to agree. When I first started teaching online, I I wanted to simulate the classroom experience as much as possible because that's the way I knew how to teach. And I don't like PowerPoint, so I don't really care about all this the fancy stuff that you see these days, like on YouTube instruction videos. I just wanted to teach online the way I would teach if we were face to face in a classroom. So that's kind of what right or wrong, good or bad, that's my approach. And I'm sticking with it, daggone it. All right, switching gears, chi-square test of independence. What we need to think here is we have, well, now we have two categorical variables. So if we have two quantitative variables and we want to analyze the relationship between the two, we use correlation techniques, correlation regression, stuff that I will teach you later. But if I have two categorical variables, then I use a chi-square test of independence to analyze the relationship. So the illustration I'm going to use here will be we have X is a belief on abortion. So what we force people to make a choice if they're going to be part of the study is they have to be either pro-life or pro-choice. And kind of something I wouldn't have done, but it wouldn't be appropriate for chi-square test of independence if I didn't do that here, would be to categorize the age. I see no, if I had ages in years, I would see no reason to categorize this in terms of senior citizen and not senior citizen, unless there was something in the literature or a goal of the study that led me to do so. Because if this was quantitative and I wanted to analyze the relationship of the quantitative variable over pro-choice, pro-life, then I would use an independent samples t-test to analyze the difference in sample means. But since we have two categorical variables, we're going to use chi-square statistics. So it's important to think about the context. And that'd be one of the things on your first exam. A priority is to give you an education research scenario, and you determine what statistical test is appropriate. But let's just dive into an example. So what we have is we have the following counts. So we call these the observed counts. So we have 239 who were not senior citizen and were pro-life, and so on and so forth. Something we need later is that we need the row totals and the column totals, and we can see that we have 883 is our total sample size. So what I want to do is I just want to demonstrate how the chi-square test of independence is carried out. And hopefully for most of you, this is just a review. Hopefully you saw this in undergrad or maybe even a previous uh, statistics course at the grad level. So we start out with uh, stating the null and alternative hypotheses. The null hypothesis is that the two variables are not related. So we say that age and belief on abortion are independent. And the alternative hypothesis is just the opposite of that. They are related. We say that age and belief on abortion are dependent, so they depend on each other. I see no reason to deviate from the standard zero point zero 0.05 alpha level. So then we start thinking about the test statistic, right? So our chi-square test statistic is the sum of the observed cell count minus its expected cell count uh, divided by the expected cell count. So we have a 2 by 2 table, so we have 4 cells, so we're going to have 4 terms in this calculation. The expected cell count is easy to calculate using very basic uh, principles of probability. We know that if these two things aren't related, then we could take the row total times the column total divided by the total sample size. So my expected cell count for the very first cell would be 488 times 435. Again, row total, column total, divided by 883 total sample size. So I get 240.41. This is just arithmetic, so I'm not going to spend a lot of time on this calculating the expected cell counts. All right. So I demonstrate this. So for the first cell, the observed is 239 minus the expected, and you can see that I write each of these out for a reason, because this 0.0083 and this 0.0079, each of these components actually plays a role later on. We call that a contributing factor. So we end up with the chi-square test statistic of 0.036. Now we switch gears to the something that I taught ad nauseum, focus on the underlying probability distribution, or the sampling distribution. And this phenomena is from the chi-square distribution. Its degrees of freedom for the test of independence is found by taking the number of rows minus 1 times the number of columns minus 1. So we have 2 rows, 2 columns, so 1 times 1 gives us 1 degree of freedom. So what we have is, we don't have any of the two-tail stuff like we do with the t-distribution or the standard normal distribution. The p-value is just calculated by the area to the right only of the test statistic. And this is super easy to do. Let me just bounce out of this and bring up R. Not sure if you noticed, but that's me scuba diving somewhere in Cozumel, I believe. I sure wish I was there right now. All right, where are we? I got sidetracked with scuba diving. So I need the area to the right, chi-square distribution. So because I need the area to the right, not below, I have to subtract it from 1. So my test statistic is 0.036. My degrees of freedom is 1. And I get a p-value of 0.85. Well, that's clearly greater than 0.05. So we fail to reject the null. So by failing to reject the null, we are saying that this statement is more believable than the alternative. We don't get into goofy statements like, well, the null is true, and we don't do that. This is all based on probability. But based on the sample data, believing that or concluding that age and belief on abortion are not related is more defensible than they are related. Now, how would we do this in R? I think this is a kind of cool approach. I'm going to show you a couple of different approaches, but I would call this just kind of diving in and getting our hands dirty, if you will. Just setting it up from a table, contingency table like we have, and just going through the process. I'm going to also demonstrate in this video how we would run a chi-square test of independence if we had data. So we'll use a data set here in just a second. All right, so first thing I need to do is set up what I would call my counts. And I'm going to set this up using the matrix command. And let's see, I need the, oh, cool. I've got them right here, don't I? So I have 239, 249, 196, and 199. And then I need to come in and let R know that I wanted to read by row. So I wanted to read the rows first, and the first row and then the second row, all right? And then I want to tell R the number of rows and number of columns that I want. And you can do counts, and you can see that we get the matrix that we need. Now, the next thing I would want to do, maybe, I don't know, I'll just show you how to do this. It's nothing that really matters. If I wanted to create row names, fingers are too fat today. I could, let's see, our rows were, I forget, what were our rows? Okay, so not senior citizen. And if I want to do column names, obviously this has nothing to do with column or pro-life. All right, now if I do counts, you'll see that everything is listed. All right, cool. Now I want to get into actually running the chi-square analysis. So it's really easy to do with R. If I use the chi-square.test command and I use the counts and use model, and you can see something kind of interesting happens here. You notice that the chi-square test statistic that we got previously, let me bring that up, was 0.036. Certainly doesn't align with what we get here, and we saw that the p-value above was 0.85. Certainly doesn't align here. The reason is the Pearson chi-square test with Yates continuity correction is the default when you have a 2x2 table in calculating chi-square test of independence. Now, if I don't want that, what I can do is I can go back up to my chi-square command and just do correct equal false. And now if I run my model, you'll see that I get the chi-square test statistic 0.036 and p-value 0.85 as I calculated by hand. Now, what should you take away from this? Previous research shows that when we use standard chi-square procedures for a 2x2, we typically get a lower p-value than we really should get. Now, and Yates came up with a continuity correction to where we could, I would say, get the 2x2 results on the same page as a non 2x2 chi-square statistic. So, and it's kind of cool. The Yates is just, if we're doing the chi-square Yates continuity correction, we still start out with the observed minus the expected. See if I can even remember this. But we subtract, or Yates subtracted 0.5 and still divided by the expected. So that's just, again, this part right here is just the Yates continuity correction, because he found in the 2x2 case that the chi-square test statistic seemed to overestimate the true chi-square test statistic. So in this case, the true for the 2x2. So in a nutshell, if we have a 2x2, I want you to always report the Yates continuity correction. If we have something other than a 2x2, I want you to calculate the standard Pearson chi-square test result. Now, once we run this with the model, we can get some kind of cool things. The first thing that I can run is the expected values. We calculated those earlier. And let me see where we actually calculated those. Right here. So 240.41, 247.59, or 0.60. Another thing that we can run that's very easy to run would be the residuals. I don't get a lot from these. All the residual does is just gives me a metric that subtracts the observed minus the expected. So it gives me just a difference of the observed minus the expected. I prefer, if I'm going to analyze the standardized residuals. And they're much more helpful. So what I would get from the standardized residual is I would see that this cell in standard errors is 1.9 standard errors uh, below, well, I should say that the observed cell count is 1.9 standard errors less than the expected cell count. This would tell me that the observed cell count is 1.9 standard errors above the expected cell count. So what we have on our radar for the expected, well, I'm sorry, the standardized residuals is, do we have any of these that are greater than the absolute value of 2? So greater than 2, less than -2. If we do, then we would think that that particular cell uh, has a high standardized residual and was very impactful in the calculation of the chi-square test statistic. Chances are, if you have a cell that is 2 or greater, then you're going to uh, end up with statistical significance. Not always. It depends on the sample size, obviously, but yeah. You know what? I was going to actually jump into the next. Yeah, I think I'm going to do that. Let's just go ahead and I'll tell you what, let's not do it. Let's end here, and then the next, I'll upload a data set, and we'll see how we handle the chi-square test of independence there. All right, take care.